This lecture will look at some examples of vector active structures, some historical ones, some more contemporary ones, and we'll look in particular at how we can sort of exploit vector active principles to make more efficient structures. So ways that we can take the triangulation and the kind of use of the network of nodes and chords and combine that with other structural principles to make structures that are even more efficient than we might expect with simple trusses. So remember from the last little lecture bite that we looked at a truss in some detail, and we noted that the triangulation and the way that a typical loading scenario worked meant that we would have a very large compressive force on the top and a tension force on the bottom. And this is something, spoiler alert, that we will deal with extensively when we talk about section active or section resistant structures in the next course. But just to remind ourselves of the kind of anatomy of a truss or a vector active structure, we have a system of triangulated panels. The sides of these are formed by what we call chords, either in pure compression or pure tension. And the kind of corners of the triangle are what we call the nodes. So this is where all the pieces of the truss connect. We have supports on the ends, obviously, but one of the advantages of vector active structures is that all of the internal stresses are resolved within the truss itself, so that the only forces we're putting on the supports or abutments are vertical loads. We don't have any of the thrust that we get with a form-active structure like an arch. So looking at some case study examples, probably the most famous historic one is from 1850, the Crystal Palace in London by Joseph Paxton. This was a structure that had to be built very quickly in only 8 months, and so Paxton's kind of genius was to figure out ways to prefabricate the entire building in cast iron and timber and glass. And the sort of genius of the thing was that Paxton figured out a module that was based on a truss system. And you can see the trusses here in the second drawing down from the top, where these elements around the edge of each structural bay are girders that are also stiffening devices. And as you can see, they're composed of triangulated panels. They're kind of low, shallow trusses made of cast iron, but they work very effectively to carry the floor loads of the Crystal Palace and also to provide some bracing. And by standardizing these, Paxton could make very lightweight structural elements that were very efficient, but also repetitive, just hundreds and hundreds of these trusses that ended up making the structure of the Crystal Palace. Because they were prefabricated, they could be assembled very quickly, and this was one of the largest volume buildings on the planet when it was finished in 1850 in time for the exhibition, and only because of the prefabrication, and only because the building needed only very light foundations since its structure was so lightweight. So here you can also see that the architectural effects of a vector active system are that you have this structure that's very porous, that's very open, and in addition to not taking up much space, you can use the leftover space for glazing, as Paxton did with the Crystal Palace. You can also use the voids within that truss for other things. A slightly more recent example, maybe also one of the best known truss systems in existence, is the Pompidou Center in Paris, this famous contemporary museum designed by Renzo Piano and Richard Rogers and engineered by O. Verep, and in particular an engineer named Peter Rice. Here is the first structural unit of the Pompidou to go up, and you can see that it's composed of these very, very long span trusses that are, again, prefabricated. They were trucked through the streets of Paris, craned into place, and assembled like a Lego building or a Tinker Toy building. Here on the left, this construction image, you can see that they're about to put this truss onto its connection there. You can see that they're made of hollow tubes, and you can see too that there's a difference in size between the tube on the top, this is going to be the compression element, and the tube on the bottom, this will be the tension element of the truss. We talked about how when we're designing compression elements, we're worried not only about crushing, but also about buckling. And so compression elements in a vector active system tend to be larger than tension elements. You might also remember that we saw a very distinct pattern of compression and tension in the diagonal chords of the truss that we analyzed. And here too, you can see that there are some chords that are in tension. These are the skinnier ones, and some that are in compression. And these are the ones that have a bigger diameter to them. Here are two scenes of the truss actually being put into place. You can see that there is what we call a pin connection in both cases, quite literally here. This, I have to say, is one of my favorite construction images of all time. You'll note the cigarette and the complete lack of safety equipment that this guy is wearing. But more importantly, you can see that this is literally a pin connection. It is a stainless steel pin that connects these two elements on the truss on the one hand and on the support on the other. And this means that the truss can actually flex. It won't impart any bending into the structure of the building itself. A pin connection is very useful because it isolates bending forces, and it makes the truss, in this case, take up all of those bending stresses internally. And that saves on the amount of material that we need to use in the building's columns. Really, though, the Pompidou trusses were not only a structural innovation, but they were really a mechanical or services innovation. The big triangular voids in those prefabricated trusses left Arups mechanical engineers with plenty of space to weave the ductwork for the air conditioning, heating, ventilation, and cooling system through the trusses. You can see in this section here that the ductwork actually passes through the voids of the truss. And here, this is a lot of this has been refurbished in recent years, but you can see here too that the space of the truss is actually occupied in some cases by the mechanical system itself. So those great big triangular voids not only save weight in the structure, but they also allow us to penetrate the structure with mechanical systems. And therefore, we're able to use what we call the interstitial space, the space between the ceiling and the floor of the building. We're able to use that for things other than just structure. We can weave ductwork and cabling through the spaces that the truss gives us, the leftover spaces. The Pompidou was famous for showing off everything, right? So seeing all of the ductwork, seeing all of the trusses. An almost parallel museum by Norman Foster and partners used trusses in a slightly different way, a slightly cleaner architectural way. On the exterior, you can see this building, the Sainsbury Center, speaks very plainly about its construction. These are two sets of vector active elements. There are what amount to columns on the sides of the building, and then a more traditional triangulated truss that goes across the span. It's something over 120 feet. You can see too, if you look carefully, that this is a truss in two directions. So it's not only a truss in the linear direction, but it has some thickness too. And this has advantages in terms of stability. It's triangulated not only in the long direction, but also in the short direction. So it's a more stable element now in two dimensions, the X and Y dimension. And this has some advantages structurally. It provides the building a little bit more lateral stability in the long direction. And you can see too that it's very, very open, and Foster's office was able to take advantage of this again to weave all of the mechanical systems into the truss itself. The other thing that was a kind of benefit was that this made construction very easy. These trusses could be fabricated in large pieces in the factory. Those pieces could be shipped together. The final trusses were assembled on site and then literally craned into place. And you can see that there are pin connections between the truss and its supporting what we'll call truss columns. All of these are tubular steel, and you can see here that tubular steel is kind of expressed very, very frankly. Look at how much air, though, how much space, how much void is in that structural system. It's a very, very deep truss, 15, 20 feet deep, but most of that is actually void. And what it's doing is it's relying on the physical distance between the two main chords, the bottom and the top chord. That distance makes the truss perform better as a bending element. Again, something we'll talk about more when we talk about section active structures. For the moment, note that these are just very, very tall, very, very steep triangles, and they're going to be able to take the bending load essentially of the truss and distill it into relatively small internal stresses within each of those members. Remember, a shallower truss, or just like a shallower arch, is going to require higher stresses in diagonal members to cope with the vertical loads. A steeper truss is going to require lower internal stresses. And so here you can see these are steeper even than the 60-degree truss that we looked at, right? More like 75 degrees maybe. Here you get a sense for the way the voids work. So in the truss columns, this is where a lot of services like toilets and side lighting and things like that are. In the top, you can see here in this sketch by Foster, they're relying on the space to get all of the ductwork, but also all of the lighting and all of the maintenance access, so that displays in the Sainsbury Center can be moved around, and they don't need to move around ladders and things to adjust the lights. They can send crews up into the system of catwalks to do that while the galleries are kind of undisturbed. Notice that Foster has a very different aesthetic than Rogers. So in the case of Rogers and Piano's Pompidou Center, you can see all of the trusses, all of the ductwork, and here there's a very, very lightweight ceiling that gives a kind of visual scrimp. Foster wants you to see the structure on the outside. On the inside, he wants you to focus on the art itself instead. Closer to home, maybe the best example of a long span truss, similar to the Sainsbury Center, is the McLeod Center, the basketball arena at the University of Northern Iowa. This kind of addition to the UNI Dome, the indoor football stadium. You can see the McLeod Center has a very, very simple square geometry. And the structure is composed, again, of long span trusses. Here you can see in the cross section the triangular panels of the main truss. Here in the other direction, the red lines are the actual trusses. And the triangles that you see here are actually just bracing. Those are designed to prevent the truss from rotating out of plane and therefore losing its depth, right, or losing its ability to carry the roof loads above it. Here you can see, too, the architects HLKB, their main concerns were a lightweight structure that would allow plenty of daylight in from the ends and that would allow views out to campus. So taking advantage of the truss's very lightweight, the fact that you can prop it up on relatively small columns, and the fact that on the inside it provides this very, very open, very almost kind of transparent sensibility to the ceiling. So here, looking one direction, you can see that the walls are predominantly glass. You can see out of the building on all four sides. And then here, notice again that they're using the depth of the truss to hold all of the mechanical space, all of the ductwork, all of the catwalks, all of the lighting, providing access to all of that, but also integrating the mechanical system with the structural depth itself, and thus saving some ceiling height, right? Making the ceiling height as high as possible by making an integrated section there. We can combine vector active principles with other structural shapes to achieve additional efficiencies. And one of the ways we can do this is we can match the truss principle to structural shapes that we already know to be very effective or very efficient. So there's a whole family of vector active structures that are actually what we call truss-arches, where we're using the shape of an arch, the gentle curve of a form-active structure, but we're resolving it with triangles, right? A vector-active structure that combines the overall performance of an arch with the kind of tactical performance, the resolution of the stresses within that arch into triangular elements. So this is a form-active structure when we kind of zoom out and squint at it. When we come in and look at the details, it's a vector-active structure. And in particular, this is a type of arch called a three-pinned arch. So this takes another structural principle, which is triangulation, and adds it to the principles of form-active and vector-active structures. A three-pinned or three-hinged arch resolves itself into three pin connections, two at the base, 1, 2, and then one somewhere near the top. There are three right there. You can imagine this being a kind of great big shallow triangle, and within that triangle, each of these two arch pieces has the ability to move or to flex a little bit without transmitting any of that bending or any of that twisting into either the foundations or into the other element. This also is a very relatively easy shape to construct. You can make two small half arches, lift them into place, pin them together at the top, and that saves you having to fabricate giant full span arches all at once. A great example of this, a really instructive example of this, is the Waterloo Terminal in London by Nicholas Grimshaw and Partners. Here you can see that it is a kind of tweaked arch shape. It's an asymmetrical arch shape to get one final track in very, very close to the lot line. So the arch has to be kind of skewed to one side. You can see it's a three-hinged arch. There's one hinge, there's two hinge, there's three hinge. And then you can see that each of the two resulting pieces are designed like an arch. So here's the curvature of piece 1, here's the curvature of piece 2. But those arches then are kind of supplemented with a vector-active truss system that gives them some depth. This allows them to work locally in bending. So this piece can take bending loads from there to there. That might be wind, or that might be snow or rain. And you can see the triangulated panels of the truss arch here. Notice on the top we have a compression element, right, thicker. On the bottom we have a tension element, thinner. And then we have compression struts, thicker, and tension cables, thinner. This one is fairly straightforward. On the other side, notice that that flips around. What's happening here is that this bigger arch is pressing down, and it's trying to basically flatten this smaller, more steeply curved arch. And so this is a rare case where the compression element actually has to be on the bottom and the tension element has to be on the top. And you can imagine why. If the arch is pushing, the big arch is pushing here, it's resisted here, then this arch is very likely to buckle outwards, and therefore we need the tension element on the outside. Again, tension element smaller, compression element thicker, compression struts here and here, tension elements between those tying them together. Waterloo also had to contend with a very tight curving site, and so all of these trusses are slightly different sizes. This was all done in the very, very early days of CAD, so there's no parametric modeling here. Each one of these has to be drawn by hand. But you can see the advantage of the truss system. Grimshaw is able to open up huge areas of ceiling to daylight. And because there's so much air in the truss is relying on dimension, not material. So Grimshaw is able to basically take out all of these areas and let you see through the structure to the skylights beyond. Very, very lightweight structure, so it can sit on relatively simple foundations, and a very, very open structure, so it can bring daylight into the space below. Here too, these are three-dimensional trusses, three-dimensional vector-active systems. So you can see that each one of these arches is composed really of two arch trusses that are laid at angles to one another, and then some struts between. And as you can see, this creates a triangle, two compression elements on the top, so sharing the compressive load there, and then one skinny tension element on the bottom. And you can imagine this triangle makes the truss stable both in the longitudinal direction, while the arch shape makes it strong in the cross-sectional dimension. And notice too, here's a pin connection. Grimshaw takes great pains to show you exactly how it works. So you can see there's a little cup here at the end of the arch. There's a cup here on the foundation end, and in between is this stainless steel pin that lets the arch rotate a little bit so that when the wind blows and the arch deflects a tiny bit, it doesn't try to twist the foundations out of the ground. A slightly more recent version of what we might call a truss cantilever beam. This is the International Terminal at San Francisco Airport, designed by SOM and completed in 2000. And you can see this is really the key drawing. SOM needed to design a huge open ticket hall down below. They wanted to bring daylight in, and they wanted to concentrate the structure as much as they could around kind of infrastructural pieces, mechanical pieces, and things like that. So you can see in each section there are 4 columns, and then there are these giant truss members here and here. Those are working like big cantilevered beams, thick at the root, skinny at the ends. Again, something we'll cover more when we talk about section active, but for the moment, just know that it's a good structural shape, balanced on the other side, and then holding up with pin connections a very, very good beam shape that's actually made out of trusses in the middle. Here's what that looks like in practice. These are the beam-shaped pieces in the center. Here you can see the cantilever trusses being supported by columns. Those columns are all integrated with these kind of ticket halls and things here, so they don't take up a lot of space internally. But look at how much daylight is coming through that long span structure. Right? This is a huge, huge span, again, a couple hundred feet. And if you look at the truss, you can see that most of the truss is obviously air. Right? It's transparent. You can see right through it because we've resolved all of the bending stresses of these elements into these chords, right? The form-active tension and compression members that separate the top and bottom chords. So here, bottom chord in tension, here, top chord in compression. All of those working together to carry the load from end to end, but to do it in a way that doesn't require a lot of material, right? That minimizes the amount of actual steel that's needed in the roof itself. There's another principle we can use which is called two-way structural action. So anytime we take a linear structure and we set it at kind of right angles to itself and we connect those very, very firmly, we get what's called a space frame or a space truss. And this is different from what we call a truss and purlin system. The truss and purlin system is how McLeod Center works. There are big single-span trusses that then carry other trusses or purlins or beams or joists without a kind of rigid connection. These work fine, obviously, right? They hold up. But if we replace those purlins instead with trusses that are set at right angles to the main trusses and fully integrated, fully connected, again with triangular panels, we get a structural type that works very differently, right? What's called a space frame. And the advantage to the space frame is that we increase the complexity of the structural network so that when we put a load onto one of the space frame nodes, that load literally gets distributed to every member in the space frame. Every member gets kind of recruited into helping support it. Just as we saw the flow of stresses through a single truss, here you can imagine that that flow is getting distributed in 2 directions, and therefore it has many, many more places that it can be resolved at the edges. Makes for complicated behavior, very difficult to calculate, but much more efficient, right? Numerically a much more efficient way to carry a load, to carry it to many, many different supports. Famously, these get used for convention halls and things like that, huge long span structures. They are the most efficient structure in terms of span to depth that we can come up with. This is an early rendering from McCormick Place in Chicago, maybe one of the best known space frame roofs, that was based on a kind of pioneering idea by Mies van der Rohe, who originally proposed a convention hall for Chicago in 1953-54 that would have used one of these two-way space frames. You can see that either way you cut the section, you get a truss. Mies was very interested in expressing the geometry of the space frame on the outside. You can see the kind of triangulars in the elevation. But the real kind of work here is being done by the triangles that are in the roof. Notice that this sits on relatively skinny columns. It's such a lightweight roof, and it resolves the stresses in two directions so well that with vertical columns and some diagonal bracing, Frank Cornacker, the engineer, is able to take the weight of such a colossal roof and to resolve it onto relatively few, relatively skinny columns in between. Other space frames relied on slightly different connections or different supports. This is the dining hall at the U.S. Air Force Academy in Colorado Springs, designed by Gertrude Kurbis of SOM, also in the 1950s. And you can see here that the entire frame is built on the ground, and the columns actually come through the middle of the space frame's voids, right? They come in the middle of the bays. What this meant was that they could actually lift the whole structure up around the columns and then basically slide the supports in like you see here, a crosshead beam. So long as we connect those columns with any of the nodes, right? We're putting the nodes directly onto the column here. We're using some struts to do that here. Here we're using a bending element to do that. So long as the columns are supporting a node, the space frame will work. And so here, even though you can see the columns going through the middle of those bays, they are actually connecting to one of the points on top of the space frame. So the space frame is kind of hung from these columns instead. And you can see Kurbis, even though the space frame is the key to it, Kurbis and SOM want instead to emphasize the kind of modular dimensions of the thing. So you don't actually see any of the triangles that are doing the real work. Nevertheless, it's a huge structural, architectural accomplishment, right? Overshadowed maybe by the more famous chapel, but a pretty important achievement and definitely an important demonstration of what a space frame can do. Those are all kind of rectilinear space frames, and in the early days, in the 50s and 60s, when everything had to be drawn by hand, space frames tended to be rectilinear. They tended to be repetitive modular elements. Today, with much more sophisticated calculation tools, and maybe more importantly, much more sophisticated kind of information management design tools, we can design space frames in kind of any geometry we want. The principle stays the same. If you have triangulated trusses running in two directions, ideally perpendicular to one another, but so long as they're at a reasonable angle to one another, you'll get this combination of two-way structural behavior, right? Just like a waffle slab. That efficient two-way structural behavior, in this case, combines with the triangulated nature of trusses to create sort of a double layer of efficiency. We can lay this out basically on any floor plan that we want. Here you can see this is actually a fairly simple space frame. It has three different axes of trusses that it uses. You can see that the columns again come up through the center of the bays, and they have these kind of tension cages that from which the roof is basically hung. But as we've gotten more and more sophisticated design software, what we find is that those space frames don't even have to be two-dimensional, right? We can warp them around three-dimensional voids, three-dimensional shapes, and get the efficiency of a different set of structural types. These start to mimic what we call surface active structures, where the gravity and the lateral loads on a structure are now resolved across the entire surface, the walls and the roof of a structure. And if you look at some of these examples, you can see that when we kind of zoom out, again, they're working like shells, something we'll talk about in future classes. When we zoom in, we see that they are actually networks of triangles. And even though we can't really discern lines of trusses that are set at angles to one another, these trusses work now not only in two directions, but also really in three directions. And so we're taking the efficiencies now of what we call shell structures. We are combining them with, if you like, the structural tactic of triangulation, right? The truss principle, to create these very, very lightweight, very, very kind of geometry responsive structures using, again, sort of hacking together a couple of structural principles. I want to finish this with one kind of final example, and that is famous geodesic domes designed and engineered by Buckminster Fuller and his associate Shoji Sadao. These were kind of proclaimed as sort of miracle structures when they first came online in the 1950s. The military, the State Department, lots of big companies commissioned Fuller to design prototypes, mass-produced geodesic domes, and some specialty ones as well. There's all sorts of kind of hype around them, but basically what geodesic domes are truss principles, again, wrapped around a three-dimensional shape. So they are like space frames, but instead of working on a two-dimensional level, they're actually working in 3 dimensions, right? They are doubly curved principle, again, that we'll talk about when we talk about shell structures. A curve in this direction and also a curve kind of in and out of the screen. And then you can see that surface is basically just divided up into triangles. And the triangles, like the simple truss that we looked at, take any load that comes into the node or any load that's applied to one of the chords and basically distribute that load throughout the entire network of chords and nodes. So just like a two-dimensional truss, but now with the complexity increased by a third dimension, right? So exponentially more routes that loading can actually take to resolve itself in the dome's foundations. I think the most interesting example of this might be the U.S. Pavilion in Montreal that Sadao and Fuller built for Expo 67. This is one of the largest geodesic domes ever built. And if you look closely, you can see that essentially it's a whole network of trusses, right? Sort of curved, triangulated trusses. Here you can see that there are 2 layers. It's basically like a dome inside a dome that's then kind of connected with triangular elements. So you can think about this like a space frame now that's wrapped around a sphere, and you're getting all of the benefit of that spherical geometry, right? like an eggshell. You're getting all the benefit of the space frame principle, trusses set at angles to one another, and you're getting all the advantages of the vector active principle, right? All of these structural bays, all of these structural modules are triangulated. And therefore, a wind load that hits any given node will get distributed through every other chord and every other node in the entire dome, so that by the time it reaches the foundations, it's essentially been distributed over hundreds and hundreds and hundreds of elements, and then dozens and dozens of actual foundation points. So a very effective way of distributing loads and therefore allowing the structure to be incredibly, almost kind of impossibly lightweight. If you zoom in and look really closely at the Expo 67 dome, you can see that Fuller is basically using the truss principles that we've talked about. So here is a node, a cast steel node, and then you can see that all of the chords are just very simple steel tubes. They had a slot cut in them, and they were just welded to little fins that stick out of each node. And this meant that Sadao and Fuller were able to cast about 17 or 18 different node shapes and then use varying lengths of tube to just connect those. This is one of the foundations, right? So this is incredibly small when you think about the size of this dome. Again, 150, 200 feet across, and it's being resolved on these relatively tiny little connections down at the base. So there are a couple of interesting kind of things about this. One is that there's so many structural efficiencies being applied to this thing that the actual members are incredibly small. So this is a couple 100 feet of span resolved into members that are really only 2 or 3 inch steel tubes. And you can also see that it's incredibly transparent. This was originally covered in an acrylic skin. And one of the great stories about it is that as engineers were working on it, they suddenly realized that they had to design the foundations not only for compression, right, to carry the weight of the dome, but they realized that on a hot day, the acrylic skin would trap so much heat through the greenhouse effect that the dome would actually exert an upward force on the foundations, right? Such a lightweight structure that it would basically work like a hot air balloon. And the foundations had to be designed to actually hold the dome down to the ground. These things got Fuller very inspired. He went on to do these experimental projects where he said if you increased the size of the dome even further, you would eventually get to the point, if you built a dome like this, the size of or the width of Manhattan, he said the elements would be proportionally so small that they would disappear, right? The dome would essentially be invisible. And inspired by this foundation problem, he proposed geodesic domes that would be so large that they would absorb so much solar radiation that they would actually kind of lift up and float. And he called these the giant projects. Purely speculative, obviously never built, but an interesting kind of end to the transparency and lightness that are possible with vector-active structures. One final note, when we started talking about form-active structures and arches, we talked a little bit about the ancient world's problem with structural shape and not fully understanding that the semicircle, while it's convenient as a way to construct an arch, is pretty far from the ideal structural shape for an arch, which would be more of a parabola, right? A catenary shape, much, much taller than a semicircle. These work, of course, but they work because there is so much weight around them that they basically hold the arch in place. Well, it's interesting to note that Fuller's domes are also circular in section, and that is still not the ideal shape for these. The biosphere in Montreal really should be a three-dimensional catenary shape, right? It should look like a rotated parabola. Fuller in the 1950s and 60s, when he's designing these, does not have access to the computer software that we do today. And therefore, to simplify the geometry, all of his geodesic domes are based on circular sections, an inefficient shape. This time, instead of the Roman bridges, which relied on their mass to make the semicircular shape work, this time, in Fuller's case, it's the fact that the domes are so light that the structural shape doesn't matter quite so much, which I think is a nice kind of interesting reversal. We've gone from form active to vector active, and we've kind of done a full 360-degree kind of turn in terms of whether structural shapes matter or not. Today, of course, with the software that you all have on your laptops, you can make space frames, you can make space surfaces, you can make space trusses in pretty much any shape you want. And one of the great advantages of the principle is that those radically curving kind of wild shapes can always be resolved into triangulated surfaces. 3 points define a plane, so depending on how smooth you want the curvature, you can always resolve any three-dimensional curving shape into a network of triangles, and therefore into a network of supporting trusses. We'll have one more set of lectures in the 346 series. We'll look at some fun structures that rely on, again, back to form-active, cables in particular, but we'll look at cable structures that achieve super long spans, and we'll look at what happens when you take a cable-stayed structure and flip it back upside down, but instead of putting it in compression, find ways to activate the surface to basically make upside-down tension structures with pneumatics.